Welcome back to all of you who have returned for yet another evening session of Tool Time stuff, and welcome to those of you who are here for your first time. The last two sessions that we spent together have focused on Emacs, which is a personal favorite of mine, but we're now going to turn some attention to some tools that are every Unix user's favorite set of sharp, small, sort of instruments to work with text on. Before I get sort of too far into this, just so you're sort of aware of what's about to happen, I'm going to talk for a little while, but I will rely upon the audience to slow me down at various points. This is to both your benefit as you're here and to the benefit of those who might be watching, recording this sometime after. I have been accused of talking quickly in lectures and classes and such, and sometimes get a bit ahead of myself, particularly for these kinds of things that I've been working with for like 15-ish years now. Some of that stuff just sort of gets baked into what you do, and so you just assume other folks know what's going on when that might not be the case. Do slow me down and stop me if you see something you want to focus on a little bit more. And mainly this is to surmount the inherent difficulty in getting acquainted with this sort of esoteric stuff, that it's oftentimes better to see someone else like put it to use at first. And that was my experience back when I was in undergrad. I was in some software engineering class, and we were working on some code base of something or other. And I was still pretty green to the whole Unix scene. I was sitting down with one of my several partners, and we were trying to figure out something about like where were these variables used in this code base. And he just punched in this little invocation of a tool called Grep that we'll talk about. And out popped this long stream of results. And I was like, what the hell? What was that? And it was at that moment that I sort of realized, oh, there's like a little world inside there that I should probably climb inside and start exploring a little bit. And that began a long, slow, grinding journey, which it's my hope to accelerate somewhat for all of you who are joining me here in person or online at a later point. Before we get farther than that, though, it's worthwhile just to mention some thanks to folks who are here to support this. Again, to Joe Finnegan, who is in the booth. He's done a very fine job recording the sessions that we've done previously to make them available to those that weren't able to make it in person. To the computer science department, because they put out some advertisements and generally pay me, wage that allows me to afford not to go out and try and bounce at bars right now, but I can instead be here with you guys to talk about more computer-y stuff. To the IMA, because they own this room and are sort of letting us use it. And to all of you who decided to show up, and all the students I've worked with in the past who have encouraged me to keep doing this kind of stuff because it's both fun and potentially rewarding in the long run. Although you have to stay awake for it at this point. We're going to start with an unusual headline, and you can see it in bold here, a drunken blog rant. I actually still go back and look at Steve Yeagy's work. He's a software engineer that started at Amazon and then moved on to Google, although I hear he has left Google now. As I was working on this stuff, looking at his more recent blog posts, and he said that Google can no longer innovate anymore. And that's about as far as I got, so I've stopped reading and continued preparing, but I am intrigued just to see what he says. But some 10 or odd years ago, I started reading his blogs, which I think he did when he moved to Google, maybe, but they're generally about sort of software engineering stuff. He has a really great tour of programming languages and lots of interesting things to say, and he, swears and says all kinds of inflammatory stuff in it, so it's entertaining, nonetheless. And one of them is about interviewing folks, and he had the following interview question that he suggested as sort of a top 5 screening questions to get folks or to get an idea of whether a particular person who's interviewing for a job at your company knows their way around the block when it comes to software tools. So his problem statement was more or less like this, and it comes from a real sort of scenario that I'll describe more of it, that you have some website, and on that website they list phone numbers. And to simplify this problem, your access as a software engineer to this website is in some Unix directory top level called website or so. And it's the case that the phone numbers for the company are changing, or the marketing department otherwise wants to make sure there's uniform format for the phone numbers, things along those lines. That maybe the company's upping and moving to some new location, so in order to maintain the website, they need to find all phone numbers, which unfortunately happen to be in two slightly different formats. One with little parens around the, I think in the US it's the area code, and one without the parens around the area code. I think in Jaege's actually formulation, this was something like it was parens in a space versus 2 dashes here, something like that, but we're gonna simplify it just ever so slightly and abuse that part. So with a large sort of website like that, with 50,000 some HTML files. In the modern era, this probably wouldn't be HTML, it'll be some codey stuff that's produced on the fly. But you get the picture. There's a lot of files. And so with a limited time span of only 2 days, it is not feasible to task even poor software engineering interns to sort of rifle through all these things by hand and see if they can find and spot with their eyeballs, as good as they are, all these phone numbers. So how does a proper software engineer handle something like this when presented with a problem? And I'll just turn to the audience for a second. By show of hands, how many of you would start digging through in your file explorer, double click on this HTML page and start to look? It's not so much of the shakes. What do you do instead? Yeah, up front, sir.
Find files, call grep with find, and you can use a regular expression inside of grep to look for those formats.
Good. All these wonderful words, the find utility, the grep utility, use of regular expressions, and so forth. And it's almost like you read this presentation material ahead of time, because that's more or less the trajectory that we're going to go on at some point. Jaege commented that during some of his interviews, he had to offer some guidance to folks because they started talking about the C++ program that they would write to solve this, that they would open up a main and then import some library that had some text processing stuff in it. And about the time they got to line 30 or so of the C++ program over the phone, he's like, is there maybe an easier way to do it? And if the answer was, well, I'm getting to that part, the easy part is to work with regular expressions in C++ and stuff like that, then probably he'd just at that point say, well, thank you, we'll let you know, and never call him back or something like that. Because really what folks are looking for with that kind of a query is whether or not you're familiar with tools that have already been written that'll solve this problem for you. Surprisingly, he stated, at least that 25 to 35% of the software engineers he interviewed couldn't solve this problem, even with help and guidance he was giving. It's like, maybe you want to try something in the command line, maybe you want to try this. And so it's my hope that everyone in the room and who eventually watches this video will answer at the very least with something like, faced with a similar problem, grep at this point. And if you happen to have find and exec and regexes and all sorts of these things, you can impress friends on that part. But if you start with, I'm pretty sure there's this command line utility that's going to help me out to make this task much, much more manageable, then this is probably a good start. And if you know something about, I can go to the manual page to look up exactly what is the regular expression syntax that grep supports, or do a little Googling to figure out how do I run it recursively, then these are all good things. I mean, if you can pull that out during the interview, it's extra impressive. But if you start with grep, this is a much better start. And Jaege went on to say, yeah, but they're probably okay, on that front. I don't think anyone would expect you to pull out what his actual solution is right off the bat, which is somewhat complex, and we'll discuss this in some more detail later on, so don't get too intimidated at this point. But part of this is just to understand that the kind of problem that he's stating there has been around for a long time. I mean, since the inception of computing. It is the point of these machines to organize information in some way and make it readily accessible. So it should not be surprising that there are a wealth of tools that have been developed over time to make that information easier to sort of get at and process. And due to the time and pressure that's been put on them over the years, the ones that are still around now are very flexible and otherwise great to use if you can wrap your head around them. So if you get that kind of an interview question, start with grep. And then maybe what we'll talk about subsequently will move you a little bit farther ahead in the candidate pool, if I'm doing my job right at any rate. To that end, there are a ton of text-based tools that are present in Unix. And we will only have some time together to talk about a few of the ones that I find sort of most useful in a general purpose sense. These are progressively in terms of sort of their utility, like grep and find, which allow you basically to look for things. And then sed, which is a sort of cheap way to do light edits on, I have some text coming in, and I want to make a little bit of transformation to it to produce some new, slightly different looking text. And we'll end tonight with a discussion of awk, which is a very sort of unloved small programming language that's been around and been sort of derided in many circles. But I find it to be just lovely. It's sort of like this gentle version of some hybrid child of C and Python that's been around since almost before either of them was around, and is sort of a generalization of the other things that are up here in terms of power. Now that's not to say there aren't other useful ones out there, and sed and awk are sort of kind of in the programming language vein, awk more so than sed, but there are a bunch of other small utilities that are worth knowing about. Many of you have seen cat, which just spits things onto the screen. It has a few invariants. For instance, you can has a couple files together, and it will concatenate all of them together on the screen. You can also do things like number lines for you, which is a cheap way to do that. Head and tail to print out the first few or the last few files, but even tail has variants that's like, oh, here's a file that's growing because it's a log file. Follow it so that every time it grows, that stuff goes on the screen. Super useful in that front. So it's worth going into sort of the Unix menagerie to look at some of these other more special purpose tools. If you're going to transform one character to another, TR is good for that. If you're working with certain kinds of column data where it's space or tab separated, cut and paste stuff are particularly useful. Sort if you have stuff you want alphabetically or numerically sorted. Unique if you want to look for in sorted data, unique entries, and split and diff and a variety of others. A lot of these are documented in various sort of man pages and in the info page for core utils. A lot of folks don't know about the info system, which is sort of an alternative to the man page system. For instance, if I wanted to know about, let's see up here, TR, I could say man tr, and you'd find that it's about transliterating or translating characters from A's to B's and so forth. You could also ask about the info page for it, and I think there might be one. Yeah, and this has some more detail and is a sort of early version of hyperlinked stuff that's present on most Unix systems. The nice part about it is that it's not just individual commands. You can say, look up the manual entry on all of the core utilities that are present on most Unix pages. This works in the terminal. It sort of follows an Emacs convention, but these things are like headings that you can click on or enter on. For instance, look at disk usage and see here are a bunch of commands that have to do with how much space things take up. If you're using info on that front, just remember that Q quits you out of this thing just as it does in most man pages. So if you want more information on all this nonsense, look elsewhere because we won't have cause to use many of these tonight, as our main attention is going to be focused on the stuff up here. Grep, find, sed, and awk, which happen to align well with part of the solution that was offered for that phone number program. So then let's start with grep, as it's an oldie but a goodie. I don't exactly, I should actually research what the impetus for the name is, but the part of that is an RE is likely short for regular expression. And what we'll find is that this little utility understands a language about pattern matching to say, here's the general form of some text I want to match. And if a specific instance of that shows up in some text file, then grep can report that it found it. This business of regular expressions is often covered in some CSI courses, possibly at the theoretical level. And I'm thinking CSI 4011 with your little DFAs and little machines and so forth. That's fine and dandy, and ultimately any regular expression engine, the thing that is responsible for figuring out if this thing matches that or not, actually requires quite a bit of theory to put together. But for practical uses in software engineering, you just have to learn a few tricks, put those together, and you'll be able to match some things. And it's our intent here to sort of talk a little bit about what those tricks look like. So as we begin then, it's good to just sort of analyze what is the anatomy of a regular expression. That could, for instance, handle some of the phone patterns that we're discussing. I'm going to put the little dash here because all the regular expressions that I'll use will match this thing. We are going to, as often software engineers do, start out with a series of regular expressions that match various phone numbers, but sort of build them in complexity so you can see the way these things grow and combine together to ultimately match either this form or this form. And later on, we'll extend this further to say, like, if I have one form, I can actually transform it into the other form without too much trouble. But we'll need an editor for that, and sed will be our choice for it. So if I was looking at matching these two things, I'd probably start with the easier one, this right-hand one, which follows an easy pattern, doesn't have any special characters. And we'll find out that parentheses are a sort of special character in regex land. To that end, if you come down and the simplest sorts of regular expressions you might consider are literals, as in 1, 2, 3, dash 4, 5, 6, dash 7, 8, 9, and then 0. This will match exactly the string as such. So if a phone number happened to match against this, be present in a text file, grep would, as we use it, report that, yeah, this file matched it, this line matched it, I'll print it out to show that it matches something like that. But you can see it's not terribly flexible on account of it has to be exactly this phone number. And if I want to punch in patterns for all possible phone numbers, I'm going to be typing for quite a while because there are a lot of them there to type in. So the point then is to broaden this a little bit, that nothing in here is special, but that means it matches exactly in regular expressions. To that end, the first sort of step along these lines is introduce some variants. So if you see in most regular expression languages, a construct looks like this, little square braces. This is usually a character range. So the meaning of this series of symbols with an open square brace and a closed square brace is that this will match one character, and it's any character that is in the ASCII range of starting at character 0 up to character 9. So this is generally be a 1 or a 2 or a 5 or a 3 or whatever else. I can repeat this several times, as in 3 times here, to match 3 digits, and any of them can be in that range, like 0 to 9. So that'd be 1, 2, 3, or 4, 5, 2, or 9, 1, 3, anything in there and that. And then the dash reverts back to literals, as in this will match exactly the dash, nothing special about that one. Move on to 3 more digits, a dash, and 4 more digits over here. So to that end, the digits here are not the only thing you could put in a range like that. Instead, you could put A to Z for lowercase, A to capital Z for uppercase, or just a collection of characters that you want to match. For instance, if you're matching just A, B, C, D, then these would be the only 4 characters that match. It'd be one of them, but it could be any of A, B, C, or D. Or if you're trying to match vowels over here, that A, E, I, O, U might constitute. But importantly, despite this thing taking up more than one character here, it will match only a single thing. And to get some replicas, then you either have to be verbose and say 0 to 9, and then another 0 to 9, and then another 0 to 9, or you have to figure out the syntax to say this thing, but repeated on that front. And that's our next level of complexity, to say, like, here's one character, could be anything from 0 to 9, but it must happen 3 times. And so typically in regexes, the curly brace notation is used to denote some sort of repetition of whatever immediately preceded it. So the way to read this guy is it will be exactly the same function as the first regex. It's just one character, 0 to 9, repeated 3 times, then a literal dash, and then another set of 3 digits, and then a dash, and then another set of 3 digits, although I should probably change this to 4 here because we'd want 4 digits to end a phone number. There are some variants on that range business as well. You can specify 1 to 3 times, or 0 to 10 times, or up to 5 times. You can actually alternate this as well to say at a minimum it has to occur 5 times, but I don't care after that. And there are also some special characters that denote 0 or more times or 1 or more times that you can pull into the mix. But generally they're shorthands for the kinds of functionality that you have here. This is then starting to look more like some flexibility, because we can get any phone number with this regular expression that fits the sort of pseudo pattern that we have up here for it. We're still missing this guy over here at this point. But I want to pause just for a moment to ask if there are any doubts in the audience. No, on par. I am curious. Oh, a doubt here, sir? Yeah.
like how does the computer exactly? What if like the number was like a special kind of number? Like what if someone used a 6, but for some reason it had a different ASCII value. It was like some
Yeah,
variant of
this is a good
6.
question. So like somehow can I write a 6 without it being the ASCII code for 6? I don't know the answer to that, but chances are very likely that this stuff would break for that. And generally, the tools that I'm talking about right now and the techniques, they're appropriate for plain ASCII text. And when you go to wide characters, as would be used in Unicode, then you want to make sure that your regular expression engine, the thing that is doing the matching for you here, is actually sensitive to those wide characters and doesn't barf on them. And I have been burned more than once by having some mostly text file have some little Unicode character buried in there because some student had a name with a tilde on it or something like that, and lo and behold, that showed up there. And most of these traditional Unix tools were written way before like wide characters were a thing, and a lot of them just barf like when it comes to those wide characters. So while I don't know of a way to write a 6 outside of ASCII, there are many characters outside of ASCII that will cause failures for this stuff. You started this question also with something interesting. Is like, how is it that this set of text here is translated to something that can match that kind of stuff? And you'd think of this as very much the same process that you would go through to take some Python code and interpret it, or that you would take some C code and compile it down to become an executable. That this set of text here, along with the special meanings, something is created from it. And it's usually with the kinds of things that you would study in a 4011. A little deterministic finite automata that zips around to different states. And some of those states are in accordance with this is a match or this is now outside of a match. It is the business of those regular expression engines to convert this text into one of those little DFAs. And anytime you would use certain kinds of language processing stuff, compilers or lexers or parsers, they are using similar techniques to that. And if you want to know more about it, I strongly suggest compilers classes. And taken in conjunction with a 4011, you'd be probably in a position to write your own little regular expression engine. And you'd find out it sucks to have to do that. And you'd be thankful for all the people who have come before us and have written really robust ones that offer these capabilities out of the box. But generally speaking, that's the trajectory you go on, is that this is essentially a mini language that has to be compiled down to something that can efficiently execute. Make sense? Did I answer your question sufficiently, sir? Okay, and maybe then some. So where we left off is we got this first pattern class over here, and to that end, let's introduce some constructs that allow us to get this second pattern over here in conjunction with the first. So let me open up this third of regular expression, which introduces something that's not useful yet, but it will be soon. This little pipe in the context of regular expressions usually means an alternation, or it's essentially an or. Match something that's according to this pattern, or something that is the exact word apple, or something that's the exact word banana. And you can see where this is headed now is if I have choices, it could maybe be this or it could be this. And these are big patterns then. We're going to be able to introduce both a big pattern for the first one and a big pattern for the second one. But generally then you can mix lots of possible things in here for regular expression, as many cases as you want. And if you've taken an OCaml class yet, then you'll have seen this is also the constructs that use for matching patterns in OCaml, which is sort of in the vein of regular expression matchings. Also, if you do any language processing, you'll see this construct used for alternation of it could be this thing or it could be this thing, and I'll put a vertical bar between them along that lines. Yeah, sir.
Don't want to be that guy, but that last number before apple is a
Yeah,
phrase.
you're right. I copied and pasted a little too frequently there. So is that what you were pointing at? The
Yes.
3? Okay, yeah, cool. It's good to have a live audience because it allows me to debug my code like on the fly too, and I'm not going to pay you for it too, so I'm getting cheap labor on that front. So with the introduction of this other construct, the little or guy, we can move on to regular expression that looks like this, which is a little bit unwieldy, but we'll get the job done. And that the or that's in the middle of this thing separates the first kind of pattern, which I'll fix again, to have 3 digits, then 3 digits, and then 4 digits. Or alternatively, it could have these parentheses with 3 digits and then a closing paren and then 3 digits and then 4 digits at the end. You notice over here that I escaped the sort of parens here. And parentheses themselves have a special meaning in the context of regular expressions. You'll find yourself often escaping them with a little backslash here, which the regular expression engine is to interpret as, no, a literal parenthesis here, a literal open and a literal close. If we took those out, they'll mean something else that we'll discuss some time later tonight, a matching group instead, which is useful, especially when you want to do some substitutions. But for moment then, this thing would work. So it would get most of what Yagi sort of wants done, like out of the way. To that end, the last sort of thing that I'll mention here is there are some shorthands. And one of the shorthands you can say that might serve us in this purpose is to say a question mark, which is 0 or 1 of the previous thing. And used in this context, that would be, here's a literal opening parenthesis. I want 0 or 1 of those, and 0 or 1 of these closing parens. And that would allow me to do the 3 digits, 4 digits, as it were. And that would match either the sort of parenthesized one or the not parenthesized one. Unfortunately, it will also match some other weird things. For instance, this badly formed number where I have an open paren but no closing paren on the number, or this other badly formed one that has a closing paren but no open paren. In cases where you have guarantees that, yeah, this text that I'm working with, it has either both parens or neither parens, then stuff like that wouldn't matter too much. But it does give you a sense that regular expressions can be a little bit tricky, and you'll want to do some testing when you derive your regular expression, actually run it and look at the outputs for it to see if they make sense. And if you have some data that you know, hey, this file has a match in it and your regular expression doesn't pick it up, then you want to investigate why it didn't match. So this has some art and some science all baked into it. So take care in that front. And this is an allusion to the fact that you can have these sort of like optional stuff in there. Pluses and stars are also common for, pluses usually mean 1 or more of something, and stars mean 0 or more of something. Sort of like the range business that we discussed before. So with regular, oh, yeah, sir.
Is there an option to use \d to indicate a digit instead?
Yeah, so we'll discuss this in a second, that there are lots of other sort of ways you can go with regular expressions. The traditional Unix tools, I don't believe, handle out of the box other shorthands. And very often you'll see, rather than 0 to 9, you'll see a \d for a digit instead. This is understood by somewhat more advanced regular expression engines, but the standard, even extended regexes that are understood by Grep, I don't believe. You have to turn on Perl regular expressions, which we'll mention in just a second. So for now, we're just going to leave ourselves with this set of stuff. But there are also a lot of other sort of shorthands for like alphabetic characters, for spaces of various kinds. And so if you get yourself into a situation where you have to do quite a bit of text processing, it's worth acquainting yourself in a given engine with a lot of those shorthands, because you'll save time and probably create more readable expressions on that front. Your follow-on, sir?
Also, I was wondering, are we assuming that these regular expressions are up using the extended flag for grep?
Yeah, so we'll talk about that in just a second. So our next sort of sample here is just to actually run grep on this stuff. So I have some files, and let me open up one of those files for you just to show. Gotta find it here. I think it'll be in here, and then I have some, phone numbers. So here's a very sort of regularly patterned phone numbers. When you Google for something like random phone numbers, several things happen. Like you actually find a site that has random phone numbers, and it's scarily that site knows I'm Minnesota, so it suggests like here are random phone numbers from Minnesota. And if you believe what they tell you, these are actually numbers that you could dial at some point. Please don't on my watch. You can see I've intermingled the pattern that we were looking for here with the parens and the lack of parens that are over there. And if I come over to a shell here and do some grepping for stuff, for instance, actually, I'm going to caret this so I don't take up more space. I'm going to grab something out of the text stuff that I had here so I can show you online here. The first sort of pass at this thing looks a lot uglier than it has to be otherwise. So we'll talk about why presently. Grep, out of the box, actually interprets most special characters as not special. So whereas before I wanted this parenthesis to be treated not specially, in standard grep, all you have to do is plop down a parenthesis. Versus if I want a question mark treated specially, the sort of standard grep reverses, so I have to escape it to say, no, treat this specially. Square braces is okay, but curlies you have to treat those specially, and so on and so forth. But if you can stomach that for the moment, then when you would actually run something along these lines, it'll show all the lines that actually match for phone numbers, rather than the entirety of the file. And you see there are quite a few in here, and we've hit both patterns that we were interested in here. So to your point, sir, of which sort of regular expression form should I prefer, well, the standard grep one involves a lot of escaping, so a lot of folks turn on the so-called extended regular expressions, which establishes the convention that we were just learning about, that things like question mark are automatically treated specially, things like curly braces are automatically treated specially, and if you don't want these parens to be treated specially, then you have to escape them. This -E option then will adjust the regular expression engine that's used by grep to take on this other form where you have to do less escaping. As you go out into the wide world, you'll find lots of other spots where these conventions subtly vary, and we'll discuss that later on. But I've almost killed myself trying to work with regular expressions at various points in languages like Java, where you have to escape everything, but to escape anything in Java, you have to have a backslash to begin with. And so to put a single backslash in, you put 2 backslashes in. If you want 2 backslashes, and you have 4 backslashes. And since there's so many backslashes for things in regular expressions, it just looks awful. And I avoided killing myself and moved back to like the Unix command line instead. So take care as you go out there, because you'll see variants along those lines. A few other sort of samples on this front then, particularly using this -E option. Grep can print out usually whole lines that have some match for something in it. So if I show you this phone numbers that's irregular, a variant of that, which was just me taking the text that was in here and merging some of it, so that some of the phone numbers appear here, but there's other text on it. Some of them appear at the end, some of them in the middle of stuff. You can see the default behavior is for the grep sort of expression to say, oh, here's a line that matches at least once. I'll print the whole line. In cases that is undesirable, that you only want to see the parts that actually match, then passing some additional options, for instance, -O to say only the matching part of it, limits what's shown even for files that have lots of stuff on the same lines to the part of the regular expression that actually match. So to that end, it's worth knowing and looking at the manual page for grep to see what are my other sort of options in terms of interpretation on this. And getting back to Yegi's sort of discussion of this is, if you want to know what files have matches for this, then it's just a matter of invoking grep in the right way to say, I don't want to see where the numbers are or the lines that they're on. I just want to know the names of the files, so list the names of the files that are associated with this. So running this on grep invocation on several files at once will lead to anything that has a match being listed as a file here, -L in this case. So if you have a whole directory of those 50,000 some HTML files, you can at least invoke a grep there to search around and list the files that are there. And we'll need to look at that recursive version, which will cause grep to go deep into directories as you go forwards on it. But this listing one is something that you'll see oftentimes used to show matching files in that front. Yeah, sir?
Flag, if you have 2 matches on the same line, let's say, would they print it on separate lines?
Yeah, you can see up here that it hasn't, because I'm working on this text file that, for instance, this first line up here has 2 different matches on it. Grep would match this first thing here and say, this line matches. The reason I would print this line is because of this number. And so since you asked only for the matching part of the line, then you'll only see that part. If you want all such matches, then you'll probably find yourself tweaking a bunch of things in terms of grep options to maybe get that, or going to a more sophisticated regular expression engine. Glocks are good for that kind of stuff. Does that make sense? Okay, so that's a good observation that this had an unintended consequence of missing some of the things that are in here, particularly if several things had on lines. But it shows one particular facet a lot of these Unix tools that we'll see over and over again, that they work on lines. And generally these are strings of text that are separated by the new line character. That in a text editor you'd see them on separate lines. And each of those lines is treated sort of separately. Like I'll do something to the line or with the line and then move on to the next line. And since in this case there was an early thing that was found to match, that's the only thing that shows up here. The later stuff we never got to. Just making sense? All right, cool. Yeah, sir.
Way to output or take grep's output and just slide it into a file right away instead of...
Yeah, I'm glad you asked that one. This is like very standard Unix stuff that if I didn't want this printed to the screen, instead I wanted any of this output into a file, you'd make use of the built-in shell redirection capabilities. So typically then as you'd run something like this and wanted to store it in some phone numbers business, then you'd use the shell redirection, this little greater than sign, which means take what you would normally print to the screen and put it in some file I'm about to name. So I just say numbers .txt along those lines. Now if I look, there's this newly created numbers.txt file, and in there is the stuff that was on the screen. We'll find that, well, I guess you'll find as you experiment more that you can do other things. For instance, don't put it in a file, pass it off to another sort of command. For instance, I could count how many of these there are, which would tell me there were 70 phone numbers in the output that were associated with it. And this spares me then the need of creating temporary files if all I want to know is some answer like that. Interestingly, grep actually has an option for that to say if you pass -c, it'll tell you this is the count of how many matches I found. But that won't generally be the case. And the Unix ability to redirect stuff from one program into another program or into a file is a very powerful thing that seems innocuous at first, but will give you a tremendous amount of flexibility to string programs X, Y, and Z together in a combination that no one's ever done before, but is perfectly natural for whatever setting you've got. Does that make sense? Cool. Good question on that front. Any other doubts before we move ahead with more greppiness? Cool. Let's see. I think we've made it through just about all of this stuff with the final sort of invocation here being the original formulation of this was a whole website with subdirectories that link like web pages down several layers deep. Grep has a recursive option in terms of its invocation. This little -r is going to search not just one file or several files named, but walk through an entire directory hierarchy, looking at all possible files that are in it. And you notice, rather than pass a file, I passed the current directory in here. To give you a sense here, if I run this in a shell in my current directory, you can see in here there's a bunch of stuff, some of which might match, some of which might not, but certainly those phone numbers were. And you see here something that's obviously named after a search directory. If I run grep in here, it'll show me everything that matched in terms of files. And if I plop down a new file, let's see, echo 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 into this subdirectory search dir / new number .txt. So there's that redirection mechanism you're asking about, used to the effect of I just want to put something in a text file that's on there. Rerun the grep, and lo and behold, down here, that search directory contains this file, new number, and that one matched as well. So useful to save you a lot of hand tweaking, just recursively down throughout the entire directory hierarchy on that front. So that is some finer points of sort of grep usage, particularly this -r option I have found useful in a number of contexts. We'll demonstrate that in just a second. So a few other options to it that you may find useful at times. We encountered this -c to say count how many times something happens. -n actually shows the line numbers, as in line 23 had this thing on it, which can be useful if you're trying to open up that spot in a text editor later on. You can invert matches to say, show me things that don't match this regular expression. And finally, you can do that at the file level to say, show me any files that don't have any regular expression or any of these phone numbers in them. That may be of interest for one reason or another. One of the common examples that I want to demonstrate to you guys is I oftentimes have this problem where students will come to me. They've been taking a class or a couple classes from me, and they were applying to grad school or applying to a scholarship or something like that, and they want to know, hey, could you write me a letter of recommendation? And I'm always like a sucker. I'm like, oh, sure, I'll do that. And then I think later on, crap, I don't remember that person at all. I don't even know if they did a very good job like in the class for me. And since I keep a record of like most of my class stuff stored someplace in one directory or another, I oftentimes am using grep just to find like who is this student. I have their email address, so let me look up their grades quickly and see which classes they've taken with me. So in such case, if you had some directory that had some CS123, CS456 grades and course files and stuff, that kind of stuff, and you just wanted to see, okay, this person emailed me, last name Farrar, search all of the CS directories, do so recursively in case like the grading stuff is buried a few directories deep or something like that. And you'd come up with some like, okay, they took these two classes from me, CS456 and CS789, did really crappy in the first one and not so great in the second one either. I might want to retract at this point my saying yes to the recommendation letter. Forget it, sorry, Mary, I don't think a 3% is going to cut it, so I'll probably email her back with the email address here to say, like, I think you should probably look elsewhere for someone else to recommend. On the other hand, Olympia, she kicked ass, so I'll say give her a resounding recommendation on that front. So this kind of usage where you can't quite remember where you put something, but you remember this text was in it, grep can be a handy way just to find stuff on that front. For those that work with source code with any great extent, this is a great way to like formulate a reg expression for where is this function that they're calling defined like in this big source tree. If you formulate your source or your reg expression right, you can troll through 10,000 C files, headers and so forth to find where is pay dirt for this function definition actually present. A lot of editors that are fancy in the IDE sort of category do that out of the box. You can right-click on some sort of usage of a function, and it will take you directly to the source where it's located. But if you find yourself in an unfamiliar sort of Unix-like environment where you don't have those nice IDEs where you can right-click on stuff, then grep can serve in a pinch and usually take you 1 or 2 minutes to figure out the right regex to figure out where that stuff is defined. Yeah, sir.
To confirm, the iflag is case insensitive.
What's that? Say again?
The iflag.
Oh, yeah. I use this one here without really thinking about it. -I means make grep's regex searching insensitive to case. So it does not distinguish between capitals and small cases. And that's so I don't have to press the shift key as I type somebody's name, and it'll find last name or email address or something along those lines. So yeah, I should probably add that one to the list up here. Blah, blah, blah. Well, oh, I had it. I keep missing it, don't I? There it is. Okay, so for the sake of completeness, case insensitive search. It's not clear I'm stalling right now because I don't. Happy? Cool. All right. So then, I think that it sort of takes us to the end of what grep is typically used for. The one sort of closing thought on that front I want to mention is something we alluded to earlier, which is that regular expressions are highly irregular in terms of their actual implementation. There's this semi-famous quote from an early computer scientist, Jamie Zinski, super cool guy. Apparently, he owns a bar in LA now that you can go drink at. And maybe if you're lucky and buy him enough drinks, he'll talk regular expressions with you. But he's attributed the quote, some people, when confronted with a problem, think, I know, I'll use regular expressions. Now, instead of one problem, they have two problems. Because first they'll have to figure out their regular expression, and second they'll have to figure out, does the programming environment I'm working in actually support the syntax I selected for it? You'll notice in Yegi's solution that we observed earlier, he decided to go full sort of out Perl regular expression. And Perl is this sort of weird language that grew up in the 90s and powered like 90% of websites until about 1989, and people realized it was awful and started converting to other things. But during its heyday, it was sort of notorious for its really powerful Perl regular expressions that were baked into the language, that the folks that put the language together really valued the ability to do powerful searching, and so had a lot of flexibility with various shorthands for things like word boundaries, \b, decimals, or sort of decimal numbers or digits using \d, any sort of white space, that's spaces, new lines, tabs, etc., baked into one sort of shorthand on that front. So to that end, you'll see various allusions to Perl-compatible regular expressions, including libraries that set it, or options that turn it on for a given tool. And this is valued in some ways if you know what this esoteric jargon actually means. Takes some study, but is, if you're going to work with text, a potentially worthwhile investment on that front. Other tools out there, and I mentioned Java in a sort of derogatory light on this front, have different syntaxes of their own for regular expressions. Some of the things we talked about apply, and others are slightly tweaked. And so wherever you are working, be cognizant of that fact, that your base set of sort of regular expression primitives may come in a slightly different form as you're working in Java or Python or Emacs or VI or other sorts of environments. And so we looked at Grep on the command line. You could probably get it to work, but it might take some tweaking, as it were. You dig? Cool. All right. Yeah, sir.
Yeah, a quick question. What's the restrictions on the file type? It has to be text file?
This is a good one. Let's see. Do I have something?
Doesn't work.
Yeah, so it depends a lot, and Grep is capable of processing binary files. Let's see if we can demonstrate this quick. Wasn't planning on this, but let's see. Here, we'll come in here. I'm getting at one of these phone numbers quick. Here's this guy. And then we'll make ourselves a C file, cprog.c. I'm going to just have a global variable in here called car* num, and we'll make it equal to this thing. And then a good old int main that does nothing. I think this will work. So if I gcc this cprog.c, that gives me an a.out. If I run that a.out, nothing good comes of it. But if you were to look at this a.out, both in binary or sort of interpreted in some other way, eventually you'd see, let's see, I got to figure out where what was the number again? Let's see if 5 starts with 507. Okay. So if I look at this thing and search for that 507, it's in there someplace. Now, it's my belief, and I'm going to hopefully convert this in a second, that this will be found as a matching file, despite it being binary, using Grep as well. So we were looking earlier at this recursive bit of business. So if what I was saying is true, then a.out should come up as a matching file here, and it does. Where exactly it's present in there is going to be hard to say because, again, Grep is looking for line breaks with the new line character and treating files as this sort of stream of lines, line 1, line 2, line 3, line 4. And since this a.out is a binary file that doesn't follow that text file convention, probably the most that you could say about it is that the Grep will say report this binary file matches that in some way. But you at least know then that string of text is present in there. And it's probably the case that Grep is treating it as like, well, this is like a file with a very long line in it, but somewhere way over here, after many, many bits and bytes and so forth, is this textual number. And so I'm going to report, yeah, it matches on that front. Does that make sense?
Yeah.
Okay, now I can't comment for sure on how this will affect like PDFs and so forth, because One thing you have to realize about PDFs is that they have different sets of encodings, so the ASCII digits for 507 might actually be in there somewhere. The PDF might have some picture, like drawing instructions to draw 507, and so the text that you'd be searching for isn't actually present in that binary file format. To that end, they're harder to process on that front. And you might want to try, if you have a lot of PDFs that you want to fish phone numbers out of, it doesn't look like you're getting many hits based on Grep didn't find it, but I can see it right there. You do something like optical character recognition that would try and convert the drawing instructions that it sees or the bitmapped image that's present there into something that's more ASCII-based text, and then Grep that stuff instead. Does that make sense? Cool, okay. So yeah, nice little detour there. But I think we're good on Grep for the moment, unless there are doubts. Cool, okay. So the set of stuff that you might search could certainly encompass text files, but generally finding files with certain properties is a useful capability. That's been around for ages and ages and so forth. So we'll spend just a minute talking about the find utility, which is good for doing something like grep recursively, but has a broader set of criteria that it can filter files on. Generally then, rather than just searching text, searching for text in some patterns, you may want to search for things like files that have a certain extension, files that have a certain type, like all the directories, or all the pipes, or all the executables, files that have a certain size that were modified before or after or between certain dates and something like that. And when you would find yourself in such a position, this find utility that's present on all Unix systems is probably going to be your go-to for it. In its simplest invocation form, it just lists all the files that are in some directory tree recursively. And this in and of itself can be kind of a useful thing that serves a purpose in some settings, although we won't have much time to go into what settings I found useful for them. But essentially, this listing then of find and then show everything that's in here is one that you will see you can apply certain transformations to all those files if you're interested in them. So find on its own just looks through, lists everything, and we'll see later on that you can apply some commands, for instance, deletion to all those things if you're so interested in, or apply things like grep to them. The sort of real power in this comes from invoking things with various options that search for stuff like find within this directory tree everything that has the .csv extension. And in that case, the output will be filtered to only those file names that match the pattern ending with .csv. I want to mention here, there are two kinds of matching that you'll see commonly used in computer science and in Unix. The first we've discussed is regular expressions, and this little mini language associated with this special thing means match this class of stuff. The other one that you'll see is Unix globs, and here's an example of one. Every time you've done an ls with a star dot something or other, you've benefited from this other slightly older and slightly more limited matching set of conventions. This means match any stuff that ends with a literal .csv. And is an alternative way to specify some sort of pattern that things can match. Most shells like bash and Z shell, they have some built-in matching capability for this kind of stuff that you'd use even on the command line. For instance, listing in here anything that matches anything will show everything and do so to some extent recursively. Listing in here all the .text files being here. Listing here everything that starts with a PH and then ends with any stuff. This is sort of like regular expressions, but has a different sort of set of characteristics to it, and is usually not honored in regular expression engines. Instead, you'd look for this thing matches Unix globs and understands that sort of sub-language there. Oh God, you're going to ask me about this, aren't you? Yeah, go ahead.
I think I know the answer, but just want to confirm. Unix globs won't match with dot files, right? Anything that starts with a dot?
Yeah, there are, well, actually, I'm not sure about that. So we could test it, but I don't want to get into like all the hidden files stuff on that part. So make a little hidden file like touch hidden. And then ls star, and I don't see hidden up here, so yeah, there's your answer. And for those of you who didn't get what just happened, like, don't worry about it too much. So just to reiterate that part, we've talked about regular expressions. There's also this other kind of pattern, globs, that are different and know the context there, and that's all I'll say on that front. Follow on to that, sir.
Just for future watchers, you could use the A flag with ls to see hidden files.
Okay, yeah, I mean, like ls has a lot of options too. Read the manual if you're really interested in that stuff. But I find myself doing this all the time. To say, here's a cheap sort of set of patterns that this name option to find will work on, and limiting names to certain extensions to find all C files, or to find all CSV files, or to find all things that start with grade or something like that, or find anything that ends with, for instance, the little tilde, which are backup files that Emacs often creates, and get rid of them. These are sort of common kinds of operations that you would find yourself using with find. Now, to get a sense more of like some of the power, we need a bigger data set than I am willing to create by hand, so instead I ripped one off. Our Minnesota Senator Amy Klobuchar announced recently that she's suspended her campaign for president. It being Super Tuesday, I decided, I'm just going to download her whole website and see what it looks like the day after that announcement. You can get it yourself if you want, although it might look a little bit different, with handy Unix utilities like wget, and this will recursively traverse a whole website and grab stuff from it. Great way to generate sets of data when you want to do some sort of text processing. Although her website is reasonably sized, had a whole bunch of really heavyweight like pictures and PDFs that are like multiple megabytes big, including her tax returns. So I mean, that's what presidential nominees and contenders are supposed to do, is put up their tax returns for people to look at. But it does interfere somewhat when you want to create a small compact set of files, because those PDFs are probably scanned in using a cheap high-res scanner, and so they're very big. And I can't actually see the text in it using Grep because they didn't do the OCR on it. So some demonstrations of that on this sort of slightly bigger data set, which you can look at it, you can see it up here. The directory here looks sort of like what we were talking about and what Yegi was talking about in his stuff. It's like, here's a giant website, and we have access to a lot of the files that are on it. Not all of them have like HTML pages. There's like no sort of rhyme or reason to a lot of the stuff that's in here. If you go, some of these directories are sort of shallow. Some of them have subdirectories beneath them. Thank God, policies has like more content to it than this sort of empty sort of stuff that's elsewhere. But to that end, this would be a real pain in the butt to handle by hand. And on that front, Unix tools are going to be extremely useful on that front. So for our first example of that, you just look for like perhaps all HTML pages to distinguish between, here are the things I might want to edit because they have text in it describing a presidential candidate, phone numbers on where to contact that contender's offices, email addresses, the kinds of stuff that you as a web maintainer or software infrastructure engineer would need to manipulate. And here's our good glob friend again, just show me everything that's an HTML page. I should mention here, modern web frameworks might not have web pages that all end in .html, and I actually went through 3 or 4 different websites, including the CS website here, to try and download stuff, and they don't give me any HTML pages because it uses this modern web framework that doesn't use HTML anymore. It uses like things that are inserted there. Seems you want to comment on this?
This is a WordPress site, if you're curious about the chaos that you're looking at right now.
Look for it. I mean, yeah, and you can tell that from the little WP content over here. WP short for WordPress. If you want to start a blog, this is it. And some people use it for presidential websites as well. So I guess that's a comment on its robustness. The university that I used to work at, our computer science site had a WordPress site as our homepage for a long time until we upgraded to something more modern. It was Python-y, but I can't remember what exactly it was. All right, so then other things, well, you can combine find with some other goodies that we've been using. For instance, if you want to search every HTML page for a phone number, very similar to the original problem state that Yegi had, very similar to what was suggested as a solution to this, here's one way you might go about doing it. Find me everything in this directory hierarchy that ends in HTML, and execute the following command on it, which is just a paste of the grep that we had before, along with a little nonsense that find requires to say this is the end of the command. And anything that happens after this might be another option to find instead. The stuff up here, like the -e and the -o, that is given as options to grep. And this little closing, so open, close curlies here is substitute the file name for whatever it is, the HTML page that you had in there. So as you'd find those things, you could run an invocation like this. That would show you all, let's see, I gotta find, sorry, up in Klobuchar. Find me all those files that are in there if I wanted to see what are the names of those files rather than just what's in there. That's changing the options to grep. So here are all the HTML pages that I have to go edit phone numbers on. And we'll see later you can actually make adjustments to those phone numbers by passing a sed invocation here as do this to those files that you find along the way. So this starts to hint at one of the powers of Unix is that a lot of these tools, they talk to each other, they communicate with each other in one form or another. And find, in this case, has built-in functionality to do something like grep on a file that's present there. You can pick arbitrary other commands here, like if you're trying to find all C files and compile them, then you could use a GCC invocation here instead. Although probably a makefile is probably a better option at that point. Yeah, sir?
The pipe operator to do the multiple commands after each other instead of the -x.
Yeah, so what you'd have to figure out then is your initial invocation of find here will spit out, here are all the file names associated with it. And if you wanted to pipe that to something, you would have to understand that this is going to come in as a sequence of files that are to be treated each like do something individually to it. There are a number of programs that do this. One of them that I'm acquainted with is xargs, which will treat everything that comes in as this is something to do something to, and then allow you to specify some command to run on that. My brother-in-law just loved xargs, and like he talked to me about the virtues of xargs over and over and over again, and I could never get it because it involves all these weird characters I have to put in and say this is where the file is going to go, and this is how you have to escape, like any other weird characters are in the command line. Because I just found that the shell itself has built-in like loops for this kind of stuff, and to give you a sense for that, this would be like for f in all of these files. So run this command, generate a list, and then loop over it. And here's where I'd put then that grep invocation here. So at this point, I can use standard shell syntax, except for the fact that here the f is a variable that's going to be assigned to each thing in this list as I loop over it. And then I'll use the $f here, substitute in whatever that variable is, and run grep on that. Yeah, syntax, because I forgot. Stupid for loop needs a do over here, and then we're good to go on that front. To that end, there are different ways to combine these things. This invocation up here that we looked at initially is probably the most efficient one because it doesn't need to store any temporary stuff. Like as find locates, here's a file that matches. I am going the HTML criteria, I'm going to invoke grep on it, and then moves on to that. Versus the for loop that I have here is going to create the entire list of all those things, and then start feeding them to invocations of grep here, which means you're missing some of the caching context in the file system as you would find something there. Probably not a big deal for this, but I can see in honking big, like gigabyte-sized data, this starts to matter somewhat, and you could turn hours into minutes with a little transformation of what we have here back up to the find that's up there. Does that kind of make sense? Okay, cool. All right, so other examples of find goodies, aside from interacting well with grep and other stuff that we were talking about, you can search based on size. So for instance, I don't care about names anymore, but I do care about size. And this is where I figured out that the most expensive stuff in terms of disk space on this website happened to be fonts. And I had no idea that fonts were so big. All these are SVG files that are some kind of like a sort of fonty sort of thing, or a picture of some kind. Pictures generally take up a lot more space than text does. If you want to know exactly, then you can run this to say, find me all files that are bigger than a megabyte. Notice the +1m there. Some variance in terms of like kilobytes, and you get to specify numbers and so forth. But you can ask then, please execute the disk utilization utility on this. Show it to me in human terms, which will then print out this is how big each file is. So as it's found to be too big, then run du on it so I can see exactly how big it is. One of the common uses that I have for this particular variant then is find all big files and delete them for me. Take care of this one because this is a fairly permanent action. We'll traverse the entire directory structure, look for all files that are bigger than a megabyte, and just toast them. And in most cases, it's not possible to recover. So be careful on that front. There are other options. For instance, we talked about date ranges. There's a whole sort of plethora of all the Unix kinds of dates like access time or change time or modification of permissions times. You can screen on all that stuff for earlier than this, later than this, between this range of stuff. But specifying dates is sort of hard on me, so I'm not going to go into that too much. And you can combine this. For instance, we could search in here for all, let's see. Find in here anything that's bigger than a megabyte and that is a .ping file. So combinations of those two filters. So this will limit the search to things that are big, things that are pings, and show me all the pictures that you'd probably be better off converting to JPEGs because it's a more compressed version of pings. And if these are I'm so curious, like what is this screenshot that could actually be there? Like, oh, there she is. Like, so you can just see that as like some political intern that's like, okay, like here I've got in my Google Photos like a picture of Amy, and I'm just going to take a screenshot of that and upload it like to the website. And like computer scientists just cringe at this because like you could have, you know, right-clicked and saved it as a JPEG. That would have saved a lot of stuff, but no matter on that front. Yeah, sir.
Just to be clear, a JPEG has absolutely no decrease in quality over a PNG file?
No, that is not correct. So if you really want to see, you know, the details here, for instance, you know, the glint on the glasses or the way this guy can't look her in the face anymore, then you would probably preserve resolution. But I guarantee to you that this picture was taken with some camera, and that camera encoded it as a JPEG. And then that JPEG was viewed probably in a web browser, and then that web browser, a screenshot was taken of it, which treated as ping. So we've already lost like a lot there. So to that end, I think my argument still stands, but I'm willing to debate further otherwise. JPEG is a lossy compression, which usually means you can squeeze some into fewer bytes. Ping is lost less and is more appropriate not for photorealistic stuff, but for drawing type stuff with a limited number of colors, in which case it's much better at compressing. You dig? Cool. Yeah, sir? Yeah, and I think that is just going to be dash m or minus m. Let's hope here. There's nothing less than a megabyte. How about h? What if I just search for anything that's less than a megabyte? Well, maybe it's not that. Okay, these all look like they're, nope, never mind. Okay, I have no idea. I'm sure there is a way, I just I don't know it, and it would involve reading the manual page for find, which, as you would pull it up, it is, you know, enormous. It goes on and on and on with all the different things that find can do. And I, you know, clearly have not read all of this, nor utilized all of it, and find myself often referring back to this manual page or just Googling quick to say, like, how do I search for less than, you know, a certain size, in which case you'd probably find your answer faster. But for completeness, this is here for you. Make sense? Cool. All right. So sometimes my guesses don't work out all right, but that's okay. I'm humble about it. All right, so we can search for things using grep to find text patterns. We can search for files with various other properties. We haven't really changed anything yet, aside from maybe deleting stuff with that delete business. Let's talk for a minute about some minimalistic sort of editing that you can get. Sed is a classic Unix tool that allows this. It's short for a stream editor. And this is sort of in contrast to one of the early Unix editors called just ed, which was this weird sort of command line thing that edited text files that as you invoked ed, you'd say something to do to a text file, and then it would do it, and they give you the command line back. This was greatly improved with the invention of like VI, where you actually had a visual like editing session instead of having to see it. But Sed is still sort of hanging around as this sort of lightweight way to create small changes in streams of text. It has a somewhat different characteristic, but has a lot of relations to grep, so we'll try and punt on those in a second. And Sed programs should usually be kept small, and we'll see that once you get beyond doing 2 or 3 things using a Sed program, you're probably better off upgrading elsewhere. My advice will be to awk, which we'll end our session together with, but Perl and let's see, Python are other sort of good scripting choices as the programs get a little bit more complex. Make sense? All right, so then let's look at what these Sed programs sort of look like. You typically invoke Sed and then specify a little program over here, which has the general flavor. There's a pattern and then an operation that's associated with that pattern. And the meaning of this is if a line matches the pattern that starts here, then do this operation to it. You can have several of these in sequence. You just put semicolons in between them, as many as you like, but I usually bail out about 2 or 3. At that point, it's like now my one-liner Sed is like 90 or 100 characters long, and I can't even see the whole thing in one screen width, and so I'm going to convert it into something else, probably awk in a lot of cases. You can run Sed then on several different files as you want, and it will process them in turn, looking at each line in turn and saying, does this pattern apply to this line of this file? If so, do this operation and spit the output for it out. If this second pattern applies to the transform line, apply this operation to it. You can leave off these patterns, in which case the operations are just applied uniformly, and so they'll apply to everything. Let's see some simple examples. So by default, if you feed a file like the Gettysburg Address to Sed and say don't do anything, it'll just spit out by default what the text file looked like to begin with. And you'll notice we're using one of those techniques I mentioned earlier. The Gettysburg Address is a little bit longer than this, but I only want to see the first 3 lines and how they're transformed for space efficiency in this way. So by default, Sed is more or less equivalent to cat, like just spit things out on that front. If you are so inclined, you can start making funny little juvenile changes, like the pattern 1 would match the first line of the text file. And then you can use a substitution, change any occurrences of the letter F to the letter P. And looking at the output then from Sed, you'll see instead of 4 score, we have poor score and 7 years ago. You can do this for alternately some regular expression match, for instance, capital F or lowercase f. And you notice here little square braces. That's the same syntax that we saw in grep for matching either of those things, just one character, but either on that front. In this case, we have also added on the little G option here, which is globally for the entire line. Do this. Otherwise, it's only the first match. To that end, let's see. Actually, I think I have this wrong. For first occurrence, let me take the G off here. Oh, I got it wrong. Shoot. I wanted to separate these two, but I guess I changed my mind on midstream. If I take off the -G, I can demonstrate this one. Let's see, we're in Klobuchar now, so I need to change up to 03, yeah, code. And I have my Gettysburg here. So set on this thing, the G will change all occurrences of it, but if I take it off, then here you'll see this second occurrence of a capital or lowercase f. It doesn't change because by default this matches only the first occurrence. So this is a really common invocation, like change everything that you see that matches this guy to this guy, and the G here just carries through to the entire line. So far we've only done this to the first line. But if I take off the 1 at this point, then there's no pattern to be matched. So this transformation of substituting either a capital or lowercase f gets applied uniformly throughout the entire text file. So if we have any over here, I guess are there any more f's? Like I can't even see. Is there an f? Oh, there aren't any more. Oh, okay, so it's all in the first line. That sucks. That's okay. We'll come down and start making more rigorous changes, like add a second rule here to say change p's to f's instead, which will get us results that look like what's down here, where you can see the major change is what was a proposition is now a proposition. And while these are sort of juvenile, they're like at a level that, okay, I can clearly see what's happening here in terms of what's changing. Finally, then, the other common use that I have for sed is to turn off printing by default. And there's a little p command here. Rather than substitute, which is by far the most common use of it, you can just say print what's on the current line. So this is a cheap way to get a line range, to say don't print by default, but instead when you get to line 6, start printing, and when you get after line 12, stop printing. So things in this range print. These will be lines 6 to 12 that are printed down here. And you can sort of further subdivide that on only print 13, only print 19, only print lines that have the word dead in them, various sort of invocations along this line. So this is sort of the first and basic utility associated with sed to make light little changes and then to screen certain lines. Gives you a flavor for what these patterns or addresses are in terms of how they apply to the text file as it's coming in, and then some of the possibilities, for instance, match regular expressions and print, match regular expressions and substitute uniformly, et cetera, et cetera. So far, so good? Okay, cool. Now, we talked earlier about the need to occasionally sort of match more than one thing. But if you were faced with the problem of making changes that are variable, then you'll probably need to extend your regular expression understanding just slightly to include a few of the following goodies. Sed can be used to modify stuff, but if I wanted to convert all of this second form of phone numbers with the parentheses into the first one, as in eliminate the parentheses from it, then I'm going to have to take some sort of additional steps on that line where sed's potentially going to be useful. A first pass at this might be just to say, okay, here as I spit out what the file looks like to begin with, there's a phone number right up top that has these parentheses. I could use this regular expression substitution business in sed to say if you match a plain opening parenthesis or a plain closing parenthesis, substitute that for nothing. And this little sort of lack of stuff in between here is indication like just get rid of those opening and closing parens. And this at first pass appears to work, that the 218 that had parentheses around it is now gone. But there's an unintended side effect here. And I'm curious, if we quick scan ahead, you see something that looks a little different about this line versus this line that sed has graciously eliminated the parentheses that were on there as well. And so this first pass, while it looked good initially, changed something I didn't want it to change. And so then we go to regular expressions where I need to match exactly this pattern of 3 digits between parentheses, 3 digits, and then 4 digits. I want to convert that to digits without parentheses. But enough of this trouble of like, well, how do I substitute in this 218 that's present there? Because in the next phone number, it's not going to be 218, it's going to be 507, and the next one after that, it's going to be 651. What's a poor sod to do? Well, improve your knowledge of regular expressions, because of course someone encountered this early on when the use of regular expressions and figure out a way to surpass it. Regular expression engines usually have a sense of a group in it, as in if you put the special character, parenthesis, not escaped this time, around some stuff, then it can be treated as here's some matching text, and you can use that later in a substitution. So this wonky looking thing here that has similar sorts of flavor to what we saw before, as in literal open paren, but then series of 3 digits, literal open no literal open paren, 3 digits, 4 digits. I've grouped these such that the first set of 3 digits here on the inside, That's one match group. The second group here is surrounded by parentheses, and the third group here is surrounded by parentheses. These parentheses aren't literal, they're just established to the regular expression engine. I'm going to use later, this is group 1, group 2, and group 3. I'm going to use them here in the substitution, just say, instead of what you had, plop down whatever group 1 was. And since it omits the little raw parentheses here, I'll just get the first 3 digits, the second 3 digits, and the last 4 digits on that front. To just make that a sort of concrete then, as I would run this more robust version of sed, substituting then in raw open paren with something in a group, closing raw paren, group 2, group 3, with these little backslash, substituting the first match group, the second match group, third match group, separated by dashes, then I get the desired effect over here. First 3 digits, no parens, second 3, last group of 4, and I didn't change any of the parens down here associated with this state business. So these match groups are terribly useful if you're planning to do transformations and what you want to eventually output is dependent in some way on the stuff that was coming in that you were matching. There are all sorts of variants for this. You can have oftentimes lots of match groups. You can have nested match groups. Sometimes \0 refers to the whole match, so you can do various things on that. It depends somewhat on your regular expression engine, again, as to what syntax you use for those things and how you access them in the substitution. So consult whatever programming documentation you're interested in. Just know that if you match something, then probably there's a way to make it available in the substitution that you ultimately produce. Question here, sir. Oh, cool. Okay. Well, see, I'm just that good. I'm like reading minds as I speak on that front. Did I answer yours already too?
No.
Yeah, I did.
Okay, yeah.
Go ahead.
Can you undo something like this?
Can you undo it?
So like if you ran it and then could you like, or is this, yeah.
Yeah, so far we haven't actually changed anything because what sed does is open up the file, start processing lines, and as it makes changes, it prints it to the screen. We'll get to that changing business in just a second, but as a stream editor, its default is to either read from a file or read from standard in, and then print its results to the screen. Using the facilities that we talked about before, you can always take those results and dump them into a file using the little like a greater than bit business. And that's oftentimes like all that one needs to do. For instance, if you came over to the shell, actually let me pull up this thing here. This guy. So running this as is will print all of the transform stuff on the screen, and then I can dump that into a better numbers .txt, and now that's an actual file, and here are all like sort of better numbers. You know, I can drop that in as a replacement for whatever it is I was doing before. Or, as we'll get to in a second, sed actually has an ability to modify things in place, which is going to come in handy when you don't know exactly where all the files are that you want to change. Does that make sense? Okay, cool. Yeah, sir?
Should actually create the files if you put it.
Indeed, yeah. Let me demonstrate here. So here's this better numbers guy. Let me delete it. It's gone now. Kill a buffer there. I'll come over here. I'll rerun that command. You can see it's going into better numbers.txt. So I'll press enter here. And over here, let me refresh the directory listing, and voila, like it's been created on that front. By default, that redirection, if a file doesn't exist, it will create one and start dumping the stuff that you want into it. It's good. Terribly handy. So. Okay, let's see. I've lost my train of thought here, so let me refer back to notes on that front. All right, so for simple like sorts of tasks and like that, sed can be useful to transform streams of text as they're coming in. Let's see one example here which combines some of the things that we saw earlier. So our initial problem statement was this phone number business. And we're now in a position, because we have a light editor, this sed business, to actually affect the changes. You'd use find to locate all the HTML pages. And then you'd probably execute sed in some way to say, find patterns that look like this, which have some set of parentheses or lack parentheses in it, and make some transformation, substitute things over here. The particular invocation I've chosen here goes in the other direction, that it will change numbers that look like this with no parens to numbers that look like this, which have the 2 parens around it and a space instead. There are a couple tricks here that are worth mentioning as well. You were asking about changing stuff. And this -I option to sed asks it to do so in place. Rather than printing the output to the screen, it will pick up the file, generate a stream that's transformed, and then plop the results back down whatever the file name was. If you're interested in doing that, it's oftentimes handy to have a backup in case you flub the transformation. And so by default then -I has a little option to it. You say .bk, it will name a set of files then html.bk, and that's the original version of the file. And the next one that's edited in this case using sed will have another backup file associated with it. So that as I would run this set of stuff here and say grep for phone numbers that look like one format, I find nothing, search for and change that set of stuff, and there they are. I can then ultimately, using a little shell wizardry, go through all the backup files and restore them to the original names if I want to backtrack on that part. So then sed used in combination with find allows you to do this entire sort of directory traversal and make those changes without ever having to visit them by hand, or without ever having to pull up some fancy GUI-based tool that sort of allows you to do this. Although it does carry some risks on this front, mitigated by those backup files. I think that's my piece on that. That gives you sort of a sense of the possibilities here associated with this. Before we leave off on sed, I just want to mention it has other features to it, but since I haven't used them in the 10-odd years I played around with it, I won't comment on them now. It doesn't have your standard set of programming language constructs like loops and variables and such, but it does have a notion of like some sort of pattern space and things that you can copy and add onto and then paste out of into the output and stuff. But usually at the point I start thinking I need that, I'm just like, nah, we're just going to do an awk instead, because it looks a lot more like other programming environments that I am accustomed to. So that's it for sed, unless there are doubts. Cool. Now for my favorite, and I did save the best for last. You should have noticed sort of that this grep business, it has some searching kinds of capabilities, and you can emulate that more or less with sed. It's like, okay, I can search for certain things and not make any transformations, and some of the functionality there is overlapped. Awk is going to feel that way too, as then everything I could do with sed, I can do with awk plus some more, because it's somewhat more general purpose, but involves a little bit more setup on that front. So let's examine a few of these things. First, the name, which I had to look up because in all my many years of using it, I didn't look it up. It's named after Aho, Weinberger, and Kernighan, who were the original authors. All of them at AT&T Bell Labs, which was this hotbed for early computer science development. I mean, they were folks that have their names associated with other really inconsequential stuff like the C programming language and the Fortran compilers that were originally there and the Unix operating system, stuff that pretty much nobody cares about, so but I can just focus on awk for the moment. What you'll notice as we start looking through it is that it looks kind of like C and kind of like Python and has some features that are sort of like them, although since it predates Python and was a contemporary with C, a lot of the sort of features there have been present in awk have been stolen by later scripting languages, and we'll see some stuff that looks like that. It also is the case that the general emphasis of awk is that it follows sed's convention, where we specify things like here's a line of text and a pattern that if it matches this line of text, commit this sort of action to it. Although we'll see this takes the form that's a little bit bigger and girthier and allows for more complex transformations to be done with higher sort of fidelity on it. Plus, awk is a Turing-complete language. Like anything you want to do with computers, you can do with awk. It has loops, it has variables, it has functions, it has associative arrays built into it. And so let's start having a look at those things. As usual, when you want to look at a new programming language, you just try and figure out how to say hello world with it. And if you were to look at a simple awk script, that would be something like hello.awk. This already says you can do more with awk because you can make scripts out of it rather than sed. You usually specify things just on the command line with it. And the simplest sort of begin or hello world program just looks like a begin with a print hello world. And those two things sort of are sort of coordinated using a set of curly braces, which will be familiar to anybody who's written C or Java or any of those other curly brace kinds of languages. If you were to run this thing, you'd have to invoke awk as a program, say here's a script, hello.awk. But oftentimes you'll see this little shebang up here, which is the little sort of hash and then the pound symbol, the exclamation mark. This is an indication that under the right circumstances, you can run this as a standalone script as well. Typically, you do that as follows. Let's see if I got this hello awk in here. Here's hello awk. Change the permissions on this thing to make it executable. Hello.awk. I can run it either by saying, here's my script, hello.awk, and it'll do it. But now, since it's also executable, I can just say /hello.awk, and it'll do its own thing, because the interpreter that the script is to be used with is mentioned up here at the top of it. Very handy, and if you drop the awk extension, this starts looking just like any other normal program. For instance, I copy that hello .awk to just hello and run hello, and voila, I have like a hello world style program like in the awk language rather than in C or Java or Python or whatever else on that front. So far so good? All right, now you can also do the sort of standard one-liner thing, which is awk, and then here, instead of giving a script file, I can say begin print hello, and this will do the same thing as before. But the reason you'd oftentimes turn to awk is that you have some more complexities, and you want to save what you're going to work on, so putting in a file starts to make sense in that front. To break this down just a little bit, this begin guy is a keyword that's a pattern. It means match the beginning of the execution. So this is sort of startup stuff, why you see it right away. And then in here in the curlies is the action to commit once this pattern is matched. This kind of a program is a little bit uncommon. Instead, you'll see stuff that looks more like the following instead. So here's a demonstration of an awk script in total. You can see the shebang up top. Here's a pattern that would match any line that has the word dead in it. The following will be done, as in print out this string, hello, this line is morbid, and this little $0, which we'll find matches the entire line. So print this text, hello, this line is morbid, along with whatever that line is. The next pattern uses a built-in $1, $2, $3. They match the first fields in a line, and this is by default space separated. So you can think of it as first word, second word, third word, fourth word, fifth word, and that goes up into perpetuity. So if you have 1,500 words on a line, then you'll have up to $1,500, which is automatically assigned to whatever the 1,500th word is. This is tremendously useful because in your Pythons and in your Perls and a lot of other places, you actually have to do some sort of splitting or execute some commands to affect this. And if you're in a position where what you want is that to be done by default, then awk is your go-to on that front. So the ask here in terms of pattern is if the second word here is equal to hollow, then do this action, which is again to print some prefix text along with the rest of the line. That's up there. And this gives you some sense of like, oh, like string equality works out of the box for awk, which is a nice sort of a feature that isn't there in C's and it isn't there in a lot of other things, but this being a text processing language is a sensible choice. Finally, then you can do things like, here's a pattern that matches if this is true at line number 3, then start matching stuff, and this automatic variable nr, which is mostly equivalent to the line number, it stops being true at line 7. So this is print the things in between lines 3 and 7. If I were to run this script on a file like Gettysburg, so I got here's patterns.awk, as you saw it, and then I ran that patterns.awk on Gettysburg, you'd see the following output. The 3 to 7 are here because of this last pattern matching those. You'll see here that this line, this is morbid, where we print out that text from up here, along with $0, which is the rest of this. It matches because the word dead appears on it, and that applies to this first rule. Also on this line, this word hollow appears as the second field, the second word on it. So this second action is committed. And generally, that's the way awk programs go. It loads up a line from the file and says, does this rule apply? If so, do this. Does this rule apply? If so, do this. If this rule applies, then do this. Then, since that's the end of the program, load another line of text from whatever the input is and repeat, like, does it match this thing? Then do this. Does it match this thing? Do this. Does it match this thing? So there's an implicit loop in here where you're looping over all the lines in the files, applying each of these things in sequence to it to get output along those lines. That implicit loop then, along with the built-in variables that split up fields and so forth, they are useful to make awk programs fairly short to accomplish a lot of tasks. So despite this not being terribly useful, you can see we accomplished a lot of sort of text processing with very little effort in terms of the awk language. This introduces you to a few of the built-in things like the automatic field splitting, the presence of regular expressions, and the use here, as said did, of regular expressions in the little like forward slash stuff, comment syntax, which is according to the shell script with the little hash business, built-in variables for the long line, built-in string matching, built-in variables to say what line number you're on, all kinds of built-in stuff. And half the fun of awk is that it's got all this stuff built in. Reading the manual page will apprise you to other things that it has built in, stuff like functions that you can run, other built-in variables that keep track of what file you're on and what number in that specific file line you're on at a given moment. The ability to skip over text to say, just I found something I don't like, move ahead a few lines of text. The ability to open up while you're processing one file, another file, and start getting lines from it instead and get the same sort of automatic variables present. All kinds of built-in goodies there that once you sort of get your head around the 2 or 4 dozen different little things that are in there, you can combine them in all sorts of interesting ways. Let me point out a couple interesting ways that I've found particularly useful, and that'll bring us to the end of our stuff. Let's see, so we got this guy, we got this guy. Printing out fields is tremendously useful in a lot of contexts. That I want to look specifically for this line, look at fields 2 and 5 and 9, or I want to print out all fields and process it in some way. So a simple little awk script like the following will go through every line and separate out and give you a chance to look at every individual word that's on those lines, irrespective of how many words are on them. So it shows you that, yeah, there is a for loop syntax built in, and if you programmed in Java or in C, then you'll be acquainted with the syntax. Start some variable someplace, iterate until some condition is no longer true, and increment something as you go ahead. A few things that will be less acquainted, NF is a built-in that tracks how many words, how many fields are on this particular line, which changes each time a new line is read in. Unfortunately, these things start from 1, so $1 is the first word, $2 is the second word, and so forth. So you adjust your thinking there with less than equals and so forth. And then you have this built-in ability to print things separated by commas, which will just put spaces in between them. So online, 4 scored 7 years ago. Come down a little ways, you'll see line 2 starts out, and we start iterating over those things. It goes on and on and on that part. Now, this may seem sort of limited in utility until you realize the field separator, the thing that determines what's the first word, what's the second word, what's the third word, and so forth, that's actually under your control. Generally, it's a regular expression, so you can say, like, this weird combination of X, Y, Z, 2, 1, 3, that's what separates words in my thing, and move that to great effect. But in other more mundane circumstances, you might find yourself editing something like a CSV, comma-separated values file. And in that case, we can take the same script I had, this print fields business, and just say, no, this is not separated by spaces anymore. This is separated by commas. And so print out each of the CSV files there. So here's this spaced name here, but it's considered the first word because now I'm separating on commas instead. And in this case, that CSV file had a uniform like 4 fields per thing, but I can use the same script just by changing field separator to get more or less the same effect on that front. The final sort of coup d'etat on this that I want to talk about is what I found has been the killer feature of awk, is that it has exactly one data structure built into it, which is associative arrays. And that's really all you need to do most interesting things. It's sort of nice in that respect because there's another modern language, Lua, that also took this approach where the only thing built into Lua is tables, which is an associative array. Those can work as numeric arrays like index 0, 1, 2, 3, 4, etc., or they can work as hash tables where, let's see, apple maps to fruits and carrot maps to vegetable and so forth. One data structure to rule them all in that respect. I didn't have time coming into this to build you a program that does the following. It goes through a text file in awk and does a word frequency analysis. Print how many times the came out. Print how many times dead was present in here. So let's do that together quickly. Let me fire up and here a awk script, and we're going to apply this to that Gettysburg address. So the first thing we'll say frequency here .awk. I want is a shebang, and I'll say bin awk. Although I'm told that I should probably be using like some environment specification because awk isn't always in this directory bin awk. I don't care about such things because if it works on my system, that's all I really care about. I'm going to want to do what I'm about to do to every line. And so there won't be any patterns up here like matches dead or anything like that. I just wanted this to be done to every line, so it's an empty pattern up here. In addition to that, I'm going to need to go through every word that's on a given line because I'm going to update it as we go through. To that end, I want to pull in the code I had just a second ago, which is going to already establish this iterating over every field that was in this thing. Instead of printing it, though, I want to do the following, which is to have counts as an array. I'm going to take the word and use that as a key. So this will be the ith word here. That's the key in it. And I'll just say here, I could use plus, but I think I'll do it long form because this will make it more apparent. Look up what's there and add 1 onto it. This is a typical increment. Actually, semicolon's optional. I can lead it off and on. Now, this innocuous statement would teach you, if you analyze it, several things. That, first, we're benefiting from this $I business that automatically I'm getting word separation. This variable wasn't declared anywhere, and the default behavior is, oh, if you're using this variable, I'll create it for you. And if it didn't have a value before, I'll by default return 0 or a null string or something like that, and interconvert between those things is fine. So with very little effort there, then I've just gone through every word, used it as a key in a hash table, and incremented a count associated with it afterwards. So that has built the hash table of counts of word frequencies so far. I probably want to print it out at some point, so I'll use the built-in end pattern, say, when you're done processing all files, do the following. Here I'll say for, let's see, I think it's key in counts. Then I will print out, let's see, key, and then just a literal colon, and then counts key, which I think, if I remember right, this is the right for each loop. So go through all the keys that are in this little associative array, assign to the variable key one of those, and then make it available in the iteration count. I think that's it. I'm not sure. And you're probably questioning this, how did you not have time to do that? That's 10 lines of code. Well, I'm a busy man, it's just like, so, okay, let's try this on Gettysburg and we'll make corrections if we need to on that front. So that, and then the file I want to process is Gettysburg. So to go through, and I think this looks about right. So Lincoln appears once. That was in the thing. I think dead, we decided that appears on 3 lines. So, oh, actually, let's check that quick. Here's Gettysburg. Over here, Gettysburg. Search for dead. There's once, there's twice, there's 3 times. Okay, so I'm worried about that. Maybe the case that we'd want to have a condition up here that would increment it. So I'd say something like if key, if not key in counts, then counts. Oh, sorry, if not I in counts, then counts equals I equals 0. Okay, so that'll initialize it. That might work. See how we do now. And since I don't feel like, I'll just search for dead here. Dead one. Oh, crap. Okay, we got burned by the comma. So this actually was right. It's just it was counted as a different word because the comma's here. Okay, I'm sure there's a way that we could solve this with regular expressions to say I want to eliminate that kind of stuff. Let's see. Here's a quick one then. Substitute anything that isn't in A to Z, or a space. Let's see, I think that's there. So that for spaces. Something like that. So by default, this G sub function takes a regular expression and applies it to the entire line, doing the substitution that's mentioned. This might have it. Oh no, I screwed everything up. Okay, what did I do? Oh no, that's terrible. Oh, of course. I want to match anything that doesn't match those things to it. Inverted. Okay, so maybe we have it now. Grep for dead. Yes. Okay. So then this would be the sort of completed frequency list. So hopefully that gives you a sense then of the utility of these text tools, the regular expressions that are backing them up, and some of the interesting things that you can accomplish with them with just a little bit of tweaking, a little bit of learning, and a little bit of experimentation, like on the fly. As usual, make sure to check your results as you're producing them so that you're ready for that interview and you can answer grep successfully. Thanks all for your attention, and I'll be around for more questions afterwards if you have any. See you next time.